In recent years, power companies have begun increasing their use of underground systems for power distribution in suburban areas. An important part of putting in these underground systems is installing the cables and maintaining them. When there are additions to existing URD areas, or when a cable is damaged, there's a need for workmen who know how to install and repair cable using cable splices. Now, to be able to make splices and other cable repairs properly, a workman has to understand how cables are constructed and how they supply power in an underground system. Primary and secondary URD cables are designed to meet very specific needs. The cable insulation and shielding that make up a typical URD cable are necessary to help the cable function more efficiently in a URD system. In this program, we'll be looking at cable design and at how primary and secondary cables are spliced for repairs or maintenance. We'll see how a typical cable is constructed and what its various layers are for. We'll look at the differences between primary and secondary cable and at how each is prepared to be spliced or repaired. We'll see how primary cable is spliced. We'll look at several different types of cable splices and splice kits. And finally, we'll take a look at secondary cable splicing and at some secondary splice kits. Now, before we get into cable design, you need to know exactly what a cable is. A cable may be defined as a conductor that is enclosed in insulation. Now, some cables have additional layers, and we'll look at those in more detail a little later on in the program. The conductor in this cable is this stranded aluminum wire. Generally, a conductor is any material that provides an easy path for the flow of electrical current. And the insulating layer is this layer. Insulation, as you recall, is a material that strongly resists the flow of electrical current. Insulation thickness is an important part of cable design. Normally, there's a relationship between the amount of voltage a cable can handle and the insulation needed to safely contain that voltage. With secondary cable, the insulation is generally applied at a standard thickness to cover the entire range of secondary voltages. Now, this can work up to a point. But when a cable is used at higher distribution voltages, the amount of insulation required to maintain the relationship would make the insulation too thick and bulky to be practical for use in a URD system. So while the conductor and single layer of insulation are enough to be considered a cable, for primary voltage URD applications, the cable design wouldn't be a very efficient one. For primary applications, the design must be changed somewhat to improve the efficiency of the cable's insulation. Now, let's see how this is done by taking a look at a typical primary cable. Now, keep in mind, different cables are designed differently, and not all cable designs may use all of the layers you see here. The cable design depends on how the cable is used. Okay, a primary cable is normally designed with several different layers. With an illustration of the cable, we can see more closely how it's constructed. Now, here we have a representation of a typical primary cable. We'll look at its different layers from the inside out. First, there's the conductor, which in this case is a stranded copper wire. Typically, primary conductors are made of stranded copper or aluminum wire. Conductors can also be solid wire, but since solid conductors aren't as flexible as stranded conductors, they're seldom used for URD cable applications. Directly over the conductor is a conductor shield. This is a layer of semiconductor material that encloses the conductor to help give it a more uniformly round shape. We'll see why this uniformity is important a little later on. Semiconductor material is conducting material with properties that fall somewhere between a true conductor and an insulator. You usually see semiconductive materials in the form of conductive tapes, paints, rubber or graphite compounds. Now this layer is the primary cable insulation. It has a high insulating property that keeps the energized conductor isolated from ground or other conductors. Two common types of cable insulation used in primary URD applications are cross-linked polyethylene, commonly called XLP, and ethyl propylene rubber, commonly called EPR. Placed over the cable insulation is the insulation semiconductor shield. It's a semiconducting layer similar to the conductor shield that covers the cable insulation. We'll be learning more about the function of these layers later on in the program. On this cable, there's also a metallic shield. Now, this layer of the cable surrounds and is in direct contact with the semiconductive shield below. The metallic shield is a conductive material, usually copper or aluminum, that can be made up of concentric wires or of metallic taped ribbon. On this cable, the final outermost layer covering the metallic shield is the cable jacket or sheath. It serves as a protective layer for the cable insulation and other shield layers, and it's usually made of a non-conductive material, such as plastic or rubber. Now remember, although each of the insulation layers we've just seen can be used in high voltage cables, not all cables are designed with each layer. The design of the cable depends on the situation and on how the cable will be used. For example, some cables are designed without jackets, and others, used on 5,000 volts or below, may be designed without insulation shields. Now, the cable we just saw was a single conductor cable, but different companies may use a number of other cable arrangements to deliver their power. You may see 3 of the single conductors we just saw laid together in a trench to deliver 3-phase power. URD cable may also come in a 3-conductor arrangement like this. Here there are 3 single primary cables, all insulated for the same voltage, and each covered with individual concentric wires. There are also cables that have the concentric and other layers jacketed to protect the concentric wires from the environment. Because URD cable can show up in several different forms, be sure to familiarize yourself with the cable your company uses in the field. Well, in this part of the program, we've taken a brief look at how primary cables are constructed. We saw that cables may have any number of different layers, with each layer designed to help maintain the cable's electrical properties. What those different layers are and how they're important to a cable's design are what we'll be talking about when we return. In the last part of the program, we saw that a typical URD cable is constructed with a number of different layers. What those different layers are and why they're necessary to keep a cable functioning is what we'll be looking at in this part of the program. Now, you'll recall that the cable we used earlier consisted of a conductor, insulation, and semiconductive layers. The cable is designed to use both a semiconductive and an insulating material to help maintain the integrity of the insulation. There are reasons for this design, and one of these is voltage stress. When a high enough voltage is applied to a cable, the insulating properties of the cable are stressed. This means that the insulation is not as able to isolate the conductor at the higher voltages. Let's see why. Here's what's happening inside the cable. If the voltage is high enough, the stress on the cable extends through a portion of the insulation, making less of the insulation layer effective. Too much voltage stress can cause insulation failure. If the insulation fails, the cable won't be able to isolate the voltage applied to it. This can result in an outage requiring cable repair or replacement. A part of the reason for the cable's layered construction is that the layers help reduce the concentration of voltage stress. Let's see how. Here we have a single-stranded conductor. The cable is shown near ground potential. When voltage is applied, the cable insulation becomes stressed. The radiating lines are lines of stress pushing outward from the conductor to the cable's insulation. Now, as you can see, the stress lines are going almost straight down at the bottom of the cable and are bending towards ground near the top of the cable. Because the conductor is stranded, there are high and low points from which the stress lines radiate. The lines travel a further distance to ground at the conductor low points because the path to ground is longer. Normally, voltage stress would concentrate in areas like this high point, where the insulation is not as thick. But by using a semiconductive shield layer, the cable insulation is given a more uniform thickness around the conductor, similar to what would be provided with a solid or round conductor. This helps reduce any areas of possible stress concentration. But although the semiconductor shield layer provides a uniform thickness around the conductor, it does not completely reduce the voltage stress concentration through the cable's insulation layer. These lines, bending toward ground potential, show that voltage stress is still present, but that it is now concentrated in the area of insulation closest to ground. This concentration is the purpose for the insulation shield layers. These layers provide a uniform ground that covers the cable insulation. You can see that with the addition of the insulation semiconductive shield layer, the stress lines are now equally distributed through the cable's insulation. Now, in addition to voltage stress, there is another problem with energized cable: stress relief or static charge buildup. When a conductor is energized, there's a small amount of leakage current through the insulation. Now, this leakage current can cause a static charge buildup on the cable's semiconductive insulation layer. If the static charge is not relieved or drained, the function of the insulation shield would be defeated. Now, the need for this relief is the reason for the cable's metallic shield layer. The metallic shield layer, or on this cable, the concentric wire shielding, serves as a drain for static charge buildup. This concentric wiring may also have other functions in the system, which you'll learn more about later in your training. Now, the metallic shield is grounded. The shield is in direct contact with the semiconductive layer beneath it. The static charge is dissipated through the shield to ground, preventing any serious static buildup. Now, in addition to the cable design working to reduce static buildup and the concentration of voltage stress, the cable is constructed to deal with other factors as well. For instance, the cable's semiconductive and metallic shield layers work to confine the electric field of the conductor to within the limits of the cable. Additionally, if grounded properly, the cable design helps to reduce the shock hazard to personnel who may come into contact with it on the job. And finally, the design keeps the cable conductor from getting any electrostatically induced voltage from other electrical cables or from other energized sources in the area. So you can see that cable is designed to do many things, all to help it function more efficiently and last for a longer period of time. Now, in this part of the program, we've taken a look at two electrical cable problems: voltage stress and stress relief. We've seen what these conditions are and how a cable's design and construction can work to help reduce stress-related cable insulation damage. Before you go any further, be sure to read over this material in your textbook and answer the questions. If you have any questions, ask your instructor. In the last two parts of the program, we saw how cable is constructed and how a cable's design can help relieve certain electrical problems. A familiarity with the theory behind the cable design is important because much of your work in the field will be installing and repairing cables. And one of the more frequent cable-related jobs is making a splice, either to repair or extend existing cable. Preparing for these splices is what we'll be talking about in this part of the program. A cable splicing is basically taking two cable ends and joining them together while making sure that the original cable design characteristics are restored. First, a cable must be prepared by removing the individual cable layers and preparing each for splicing. Now, it's important that when you're doing this, the layers below the one being removed not be damaged. Nicking the insulation can weaken it, thus defeating the purpose of the splice. It's also important to keep the splice area free of contaminants that could create a conductive path over the splice. Conductivity over the insulation can defeat the insulation's purpose and make the splice weak or ineffective. Now, for the splice to be effective, it must have the same design characteristics as the original cable. This means a splice must be installed that provides the same voltage stress and static relief properties as the original cable. Now, how the cable splice is prepared depends on many things. The cable design, its type of insulation, and the type of shield can all affect the type of splice and how that splice is prepared. To make sure the workman prepares the cable correctly, he needs to use a specific set of directions. To see how a cable is prepared for splicing, we'll watch this workman as he prepares a single conductor primary URD cable for a tape splice. All of the necessary procedures have already been followed for de-energizing, grounding, and testing the cable for dead. Keep in mind that the directions we'll see the workman following are for the specific type of splice he's preparing. Now, since cable preparations may vary, not all of the steps we'll be seeing may be necessary for the type of splice you're preparing. So be sure to check the directions carefully, because after a splice is begun, a misunderstanding could lead to cable damage or to having to redo the splice. Okay, now let's go back to the job site to see how the splice is prepared. The preparation process is done in several steps. The first step is training or moving the cables into their final position. Now, this is done for several reasons. First, training can make a work area more accessible. In vault situations, for example, cables may be trained along a wall rather than hanging free to make the vault area more accessible. Secondly, training to increase the cable slack can reduce the mechanical strain placed on the splice area. Most splices aren't designed for heavy mechanical strains. Finally, training the cable before making the final splicing cuts should help reduce the chance of moving the conductor after cutting it. Moving the conductor after cutting it can cause conductor strands to become uneven, causing a weak point in the conductor splice. The other part of preparing for the splice is making the final cut of the cable ends. This involves making precise measurements and following the directions carefully. And remember, the steps we're seeing here can only be used for this splice. Before cutting the cables, the workman cleans the cable jackets at the splicing area. This is to remove contaminants such as dirt and wax. The cables are overlapped and marked at the center line of the splice on each cable. The overlapping is done to make sure there is enough of the concentric wire to splice later. If there's no slack and the cables can't be overlapped, additional concentric wiring may have to be spliced to the existing wires. Following the directions, a measurement is then taken from the center line and marked on each cable. Then the workman lightly scores the cables, making sure not to damage the concentric wires. Then a single strand of the cable's concentric shield is stripped back to make removing the cable jacket easier. The cable jacket is then peeled back carefully and removed down to the mark the workman had made earlier. Then the loose concentric wires are folded back to the cable jacket and twisted together out of the splice area. Now, since the original mark on the cable was cut off, the workman now takes another measurement on the cable's center line to enable him to make the final cable cut. Then the cables are cut on the center line using tools like a cable cutter or hacksaw. The directions say that the workman is then to take another measurement and place his next mark on the semiconductive shield layer. The semiconductive shield is then removed at the mark. If a knife is used, the semicon layer is scored lightly at the mark and down through about half the semiconductor layer's thickness. Then over to the end of the cable, making a weak point in the layer. Extreme care must be taken not to score or nick the cable insulation below. It can then be removed by pulling and breaking at the weak point. Now, there are also other special tools that are specifically designed to remove the semiconductive layer. These tools may be used instead of the knife, and if company procedures call for their use. The next layers to be removed are the cable insulation and conductor shield layers. Following the splice instructions, the required distance is measured. Several tools and methods may be used for removing these two layers. First, a knife can be used to cut halfway through the insulation and then down to the end, making a weak point in the insulation that can then be pulled apart and removed. Another method, used with XLP and EPR cables, is to use a nylon string. The string makes a circular cut through both the insulation and the conductor shield layers, without damaging the conductor. Then a knife is used to mark down to the end of the cable, and the insulation is removed. Or, as an alternative to both of these methods, there are also special tools designed to remove these layers. Whichever method is used, the conductor shield layer is removed along with the insulation layer, leaving the bare conductor. Now, the next step in preparing for a tape splice is tapering or penciling the cable end. Now, this accomplishes several things. First, it makes for a smooth transition between the cable insulation and the insulation that will be applied in the splice area. Tapering also helps the insulation of the splice area cope with voltage stress. The tapering can be done in a couple of ways. If a knife is going to be used, a protective layer of tape should first be placed over the conductor to protect it from being nicked accidentally. By using the knife, the workman cuts the cable to the desired slope. The knife is just one of several tools that can be used to pencil. Whatever method is used, though, it's important that the cable conductor not be nicked or otherwise damaged during the process. Now, after the penciling, what remains is a cable that is ready to be spliced. In this part of the program, we've seen a workman prepare a single conductor jacketed cable to be spliced. And we saw that the preparation procedure involves training, cutting, and preparing the cable so that when it is spliced, it will retain its original electrical characteristics. Now, when we come back, we'll see our prepared cable spliced using a tape splice. For now, read over the material on cable splice preparation in your textbook and answer the questions. And if you have any questions, be sure to ask your instructor. In the last segment of the program, we watched the preparations for a tape splice on a single conductor jacketed primary cable. Now, in this part of the program, we'll see the same workman as he completes the tape splice. One of the first steps in making a splice is joining the conductor ends with the connector, sometimes called a sleeve. The connector fits over the ends of the conductors, and high-pressure tools are used to squeeze the connector on at both ends, bonding it to the conductor. EPR and XLP insulated cables usually use compression connectors. Using another type of connector, such as one requiring heat for its application, can damage the insulation. Now, before we see the splice made, let's take a look at a couple of the tools used to apply the compression connectors. Two of the most common types of application tools or presses are the mechanical press and the hydraulic press. Mechanical presses use the mechanical advantage of their handles to apply pressure to the connector, while the hydraulic presses use hydraulic pressure. Now, generally, the size of the compression connector determines which type of press will be used. Mechanical presses are used for the smaller sized connectors, and hydraulic presses are used for the medium and larger range connector applications. Now, most presses have sizing inserts called dies that allow the press to be used on different size connectors within a certain range. You must be sure you're using the correct press and die for the connector you'll be working with. Now, this sizing information can generally be found on the connector itself, or it may be written into the manufacturer's instructions. Connector instructions generally come separately from any other splicing instructions. With the correct equipment and the instructions close at hand, you're ready to begin the splice. Now, it's important to remember that the cable splicing you'll be seeing here is unique to this situation and is only intended to be an example. Be sure to pay close attention to the instructions for your splice. The workman begins by cleaning the conductor with a wire brush. This helps to ensure good electrical contact between the conductor and the connector. He then checks his connector to see what type of die he should have in the press. Then he'll check the dies in the press to see that they're correct for the job. The connector is then applied by placing it over the end of one conductor, making sure the conductor is fully inserted into the connector. Following the manufacturer's recommendations, the workman will apply the connector to the first cable end. He makes the required number of compressions in an outward direction from the middle of the connector. This ensures that when the connector metal expands, it expands away from the midpoint of the splice. He then crimps the second cable in the same way. Some manufacturer instructions may also indicate that the press be rotated during the compression process. This helps keep the connector straight during the operation. Now, after the connector is compressed into place, the workman uses a file to smooth any sharp edges that may have been created from the pressing process. Next, the penciled cable insulation has to be smoothed out, and all traces of semiconductive material must be removed. An approved solvent and non-conductive abrasive cloth or sandpaper may be used for this. Then the connector is wiped clean of any metal shavings or particles. Using solvents and an approved cloth, the cable insulation is then cleaned. This is done to ensure that the splice is clean, because contaminants could supply a conductive path between the conductor and the insulation shield layers. Because the solvent can dissolve the semiconductive layer, when you're cleaning the cables, be sure not to re-clean the cable insulation with a contaminated rag. Doing this could create a conductive path. The workman then wipes his hands to rid them of any conductive contaminants before beginning the tape application. The first layer of tape to be applied is the semiconductive tape, which will replace the conductor shield layer of the cable. The entire connector and the exposed conductor are covered as directed in the splicing instructions. The next layer is a high-voltage rubber insulating tape. Before applying it, the workman measures the connector diameter to calculate the insulation tape buildup. He'll then adjust his calipers to measure the insulation tape's final thickness. He can then spot check the cable as it's wrapped for the correct amount of insulation tape buildup. Beginning on the connector, the workman wraps half-lap layers, taping over the connector and all of the exposed cable insulation. As the tape is wrapped, it is also stretched to maintain a tight, uniform layer. The tape should be stretched according to the splicing instructions, and even tension should be applied to get a uniform tape density and thickness. Now he'll wrap the tape over the splice until the splice diameter is at the thickness required by the splicing instructions. Next, a semiconductive tape is applied to replace the semiconductive insulation shield. This evens out the voltage stress in the insulating tape. The semiconductive tape is applied according to the instructions over the insulating tape and over the cable's semiconductive layers to form a continuous semiconductive layer over the splice. Now, in some cases, a layer of copper shielding tape is applied. When this is done, it covers the semiconductive tape and overlaps the concentric wires to give the splice additional stress relief properties. To make contact with the concentric wires, some splices use solder, a metal wire with a low melting point. Heated with an iron or torch, a chemical agent called flux helps the solder to adhere to the metal. Check your instructions for the correct type of solder and flux. Next, a layer of rubber tape is applied over the copper shielding. Its purpose is to protect and prevent the copper shielding from damage. Now, the last step before replacing the cable jacket layer is splicing the concentric wires together. The ends are brought together and then brushed clean to ensure good electrical contact. A compression connector is used to join the concentric wires together. Again, instructions should be checked for the correct press and die and for the number of necessary compressions. After the compressions are made, the ends are trimmed and then taped to protect the splice area from any sharp edges. Next, the workman applies a coat of rubber cement to seal the ends and to help keep out water. The next layer to be applied is made of rubber insulating tape. This layer is applied over the concentric wires, overlapping the cable jacket according to the splicing instructions. A layer of plastic vinyl tape is also applied over the high voltage rubber splicing tape so that it is overlapping onto the cable jackets. The rubber and plastic tapes replace the original cable jacket and help protect the splice from environmental hazards. The tape splice is now complete, and the cable's original design characteristics have been restored. Well, in this part of the program, we've seen what goes into the making of a typical tape splice on a single conductor primary cable. Although directions can vary somewhat, the splice we saw is typical of the ones you may be doing in the field. Now, in the next part of the program, we're going to look at another way of applying splices that uses prefabricated splice kits. In the meantime, though, read over the discussion of the cable splice in your textbook and make sure you understand each of the steps. While the splice we saw installed in the last part of the program is perfectly good, in many instances, a simpler method called a splice kit can be used. Now, a splice kit, as the name implies, is a kit containing all or most of the supplies needed to install a splice. The kits save time by having prefabricated pieces that take the place of much of the work a crewman has to do when preparing a splice by hand. The kit, like the hand-prepared splice, is designed to restore a cable's insulating and voltage stress properties. Now, in this part of the program, we'll be taking a look at two kinds of splice kits: a slip-on splice kit and a heat shrink splice. The slip-on splice basically just slides into place after the conductor splice has been made. The heat shrink splice uses heat to shrink different sized tubes over the cable. The tubes provide the layers of insulation and restore the cable's ability to handle voltage stress. With both of these splice kits, a set of detailed instructions will be supplied along with the conductor splice. Now, it's important, as before, that the directions be completely understood and followed to the letter to get the required measurements and to ensure that the splice is installed correctly. Now, when you're using a splice kit, there are several things to keep in mind. First, during the preparation stages, the layers of insulation below the one being removed must not be nicked or damaged. Secondly, the manufacturer recommendations should always be followed to achieve the best possible splice. And thirdly, you'll always want to make sure that the splice is clean and free of contaminants that could cause a conductive path within the splice. Before you begin, check to make sure that the kit you're using is the correct one for the job. The kit directions can also help you determine the tools you'll be needing for the job. Now, after you've read and understand the splice kit directions, you can begin to prepare the cable for a splice. Begin the preparations by unwinding the concentric wires and tying them back with wire or tape. Doing this before making the final cable cut assures enough wire to allow the concentric wires to be reconnected later. Next, remove the semiconductive shield layer at the recommended distance from the cable ends. Then the cable insulation layer is removed at the proper distance. Notice that the tool being used doesn't cut completely through to the conductor. Now the workman double checks that the tool and dies are correct for the job. After this, the compression connector can be installed and crimped into place on the first cable conductor. The insulation is then cleaned and wiped with an approved cleaning solvent or with the cleaning pads that may be supplied with the splice kit. Some insulation types may require that a non-conductive sandpaper be used. Then a small amount of silicone grease, which may also be supplied with the kit, is applied to the cable's insulation and to the semiconductive layer. The grease provides lubrication to ease the installation of the splice body. The workman then slides the splice body over the end of the cable. To keep the splice area clean while he prepares the other cable, the workman places the splice kit box over the splice body in the ditch. He prepares the other cable using the same steps. He then uncovers the first cable, fits the second cable conductor into the compression connector, and makes the compression. Now, to smooth out any rough edges, the connector is filed and then cleaned to remove any metal shavings from the splice area. The workman then takes a small amount of silicone grease and recoats the splice and the cable insulation. Then the splice body can be positioned over the conductor splice according to the splice directions. And for the last part of the splice, the workman will reconnect and splice the concentric wires. The wires are first positioned. Then one wire of the concentric layer is connected to the grounding eye of the splice body. Now, this is done to ensure contact between the concentric and semiconductive layer of the splice body. The remaining concentric wires are cleaned with a wire brush to ensure good electrical contact. Finally, the concentric wires are spliced with a compression connector. This slip-on splice is one type of splice kit, but in recent years, technology has brought about the development and increased usage of heat shrink splices as well. Now, the heat shrink kit differs from the slip-on in that it uses tubes rather than a one-piece molded sleeve. The tubes are heated to shrink over the connector, forming a moisture-tight seal and providing the necessary insulation and voltage stress equalization. At the site, the workman first reads the splice kit directions carefully to familiarize himself with the kit and the splice procedure. Then, as before, the cable is cleaned with cable cleaner and a clean cloth. In addition, the cable ends are prepared according to the splice kit instructions. Before the connector is compressed, the tubes are placed over the conductors. After cleaning the splice area, stress control putty is applied to the cable's conductor and then along the edges of the semiconductor layer. The putty placed on the conductor splice is applied to the same thickness of the cable insulation, along with the first of the 3 heat shrink tubes. The putty provides the voltage stress handling properties of the original cable. Now, after the putty is applied, the smallest diameter tube, which is the stress control tube, is centered over the conductor splice. Using an approved heat source, in this case a torch, the workman starts the heat shrink at the center of the splice and works outward to both ends. The heat should be applied with a brushing motion. This helps to make sure the heat shrink material is not scorched or blistered. You'll also want to make sure that the direct flame of the torch does not contact the cable's semiconductive material so that it is not damaged. Now, 2 layers of a red sealing putty are then applied to the ends of the first tube. The middle tube is then applied with heat in the same manner. Before the last tube is applied, 2 pieces of protective foil are placed at the end of the sealing putty to protect the cable insulation and the semiconductive layer from the open flame. The last and largest tube is then centered over the splice, and the heat is applied to shrink the tube over the splice area. After the heating process, the protective foil is removed. The workman now takes a thin coil of spring steel and wraps it around the last tube and over the concentric wires. This guarantees direct contact between the semiconductive layer of the last tube and the concentric wires. Then the concentric wires are joined together and spliced as before with a compression connector. If the cable originally had a jacket, as this one did, an additional tube may be applied over the splice tubes and over the concentric wires to provide the protective properties of the jacket. This additional tube is applied just as the others were. Or, as we see here, it may be a jacket like this, designed to wrap around the cable and be secured with a zipper-like metal clip before it is shrunk down. Well, it seems like we've covered a lot of very specific material in this part of the program on preparing and using slip-on and heat-shrink splices. Now, keep in mind that the directions we've seen being followed are specific, but only for the splices we saw. Your procedures may vary depending on the type of splice kit you're using and on the type of job you're doing. The work that we've been seeing up to this point is for primary cable splicing, but occasionally splices have to be made on secondary cables as well. In the last part of the program, we'll see what some of the differences are between primary and secondary cable, and we'll see 4 types of splices applied to a secondary cable. As we mentioned at the end of the last part of the program, all the cable splices we've seen up to this point have been on primary cables. In URD systems, though, secondary cables may also have to be spliced. Now, secondary cables can be spliced using many of the methods we've seen before, but because of the voltages carried by secondary cable, the cable design characteristics are somewhat different. In this last part of the program, we'll take a look at these differences, and we'll see how 4 typical splices are applied to a secondary URD cable. Now, the 4 splices we'll see are the mechanical, heat shrink, cold shrink, and rolling ring seal. Now, before we get to those splices, however, let's talk a little about how secondary and primary cables differ. You can see right away that the secondary cable has fewer layers than the primary cable we've seen. The cable is designed with fewer layers because secondary voltages don't demand as much from the cable construction. Now, for instance, because of the lower voltages, there isn't as much voltage stress on the insulation layer. This reduced stress means there's no need for the conductor semiconductive shield. The reduced voltage stress also means there's no need for the semiconductive insulation shield layer. Without this layer, the metallic shield or concentric wire layer isn't needed for stress relief. Now, some secondary cables do have a layer of concentric wire, but on these cables, the layer serves as the secondary circuit's neutral connection and not as a bleed-off for static from the semiconductive layer. Now, if the secondary cables in your system do have concentric wires, remember that they'll have to be spliced as well after the cable splice is completed. Without the 2 additional layers, you can see that the secondary cable is basically just composed of a conductor and a layer of insulation. The conductor, like the primary cable conductor, is usually made of stranded copper or aluminum. And this is the insulation layer. Now, as you might expect, because secondary cable design is simpler, secondary cable splices are also much simpler. We'll look at 4 of these splices, 3 of which use compression connectors. The 4th type uses a mechanical connector that has a slotted, threaded bolt and nut arrangement, commonly called a split bolt. Now, the conductor ends are inserted into the slot, and the bolt assembly is then tightened. To apply the split bolt, the cables are first cut so that they overlap the width of the connector. Then the insulation is removed from each cable, far enough back to allow room for the connector installation. The connector is then placed over the cable ends, hand tightened, and then more firmly secured with a wrench. To make sure the connector is on tightly, the workman taps the cable or connector and then retightens the split bolt. Around the splice, the workman places 2 pads made of an insulating putty material. The pads are wrapped around the connector and the exposed conductor and then adhered to each other. The pad is wrapped with a layer of plastic tape to make a better seal around the splice, and the splice is complete. This split bolt splice is usually just used as a temporary fix. A more permanent type of splice uses a heat shrink process similar to the one we saw used with the primary cable earlier. Now let's see how it works. First, the cable ends are cut so that their ends are butted together, not overlapped. Then the cable insulation layers are stripped back far enough to allow room for the compression connector. Before the compression is made, the workman slides the heat shrink tube over one of the cable ends and wire brushes both cables. Then the compression connector is applied, using the appropriate tool and die as before. Again, the compressions are started in the center, and the workman moves outward toward both ends of the conductor. After making the proper number of compressions on the connector, the workman smooths out any rough edges and cleans the splice. With the heat shrink tube centered over the conductor splice, the workman uses an approved heat source to shrink the tube over the splice using a brushing motion. The heating process continues until the tube is tightly adhered to the cable insulation and is smooth and wrinkle-free. As a further indication of when to stop, a white sealant will appear at each end of the tube. Now, just as with the primary cable heat shrink tubes, there are variations on the secondary tubes. This type may be used for an insulation repair, when only the insulation layer has been nicked and there has been no damage to the conductor. It uses a heat shrink material that simply wraps around the cable insulation, is held in place with a clip, and is then applied with heat. A tube that's similar to the heat shrink is the cold shrink. Here, the workman has already placed the cold shrink tube on the cable ends and made the compression splice. The cold shrink splice used here is a rubber tube with a plastic core which has a tab coming out of one end. To apply the tube, it is first centered over the splice. The tab extending from the tube on the other end is then pulled. As this is done, the tube shrinks over the conductor to form a watertight seal. Now, on this particular secondary cable, there is a concentric neutral layer. To complete the job, after the connector splice is made, the workman must reconnect the concentric wires, as we've seen before. Now, the last type of splice we'll look at is the rolling ring seal splice. The rolling ring seal uses rubber O-rings and an insulating tube. To install the splice tube, an O-ring is first placed on each cable at the recommended distance. And as with the other splices, the rolling ring tube will be installed over a compression connection. The insulating tube is then slipped onto one cable over the O-ring and rolled down the cable to make room for the conductor splice. Then the compression splice connector is installed as before, according to the splicing instructions. When the compressions are complete, the insulating tube and the O-ring are rolled over the conductor splice and over the O-ring on the other cable. In the tube's final position, the O-rings will be on the cable insulation and under the insulating tube, making a watertight seal over the conductor splice. Well, as you can see, the simpler secondary cable design means the secondary splicing procedures can also be more simplified. We've just seen 4 secondary splice applications: the mechanical connector, heat shrink, cold shrink, and rolling ring seal splice. We also saw some of the differences between primary and secondary cable and how those differences affect the design and construction of the 2 types of cable. In this program, we've taken a look at why cable design is important. We also saw how this cable design can be maintained when a cable needs to be spliced for repair or maintenance. And we saw how several of these splices can be made and the tools that are needed to make them. The job of cable splicing within URD systems means you have to have an understanding of cable construction and design, as well as a thorough knowledge of the reasons behind this design. Now, with this understanding of the basic principles of cable design and splicing, you should now be better prepared to perform splices in your company's system.